Welcome, dear students. Now we discuss about Lagrange's equation of motion, second kind, from Advanced Mechanics, Semester 6, B.Sc Honors in Mathematics, University of Calcutta. Derive the Lagrange's equation of motion of the second kind, or simply Lagrange's equation of motion. Consider a rhombolic holonomic system having capital N particles and k holonomic constants. Thus, it had small n is equal to 3n minus k degrees of freedom. To small n, generalized coordinates q1, q2, qn, the coordinates transformation equation in terms of generalized coordinates, then ri vector equal to ri vector a function of q1, q2, qn, comma t, I equal to 1 to capital N. Equation 1. Velocity of the ith particle in terms of the qj is given by vi vector is identically equal to ddt of ri equal to summation over j equal to 1 to small n del qj ri vector qj dot plus del t ri vector. Equation 2. Consider an infinitesimal virtual displacement delta ri vector at a particular instant t. Then delta ri vector equal to summation j equal to 1 to n del qj ri vector delta qj plus del t ri vector delta t is equal to summation over j equal to 1 to small n del qj ri vector del qj. For virtual displacement, this del t ri vector delta t equal to 0. So this term is 0. So delta is the virtual displacement, equal to this. Now, if the ith particle is acted upon by an applied force Fi, capital Fi vector, and dropping the superscript small a, and if minus pi dot vector be the reversed inertial force, then from D'Alembert's principle we have summation over I equal to 1 to capital N bracket capital Fi vector minus pi vector dot bracket close dot delta ri vector equal to 0. Equation 4. This equal to put this value of delta ri from equation 3, this summation j equal to 1 to small n del qj ri vector delta qj. So put here this, and after simplification we get this I equal to runs from I equal to 1 to capital N, but j runs from 1 to small n. This equal to I equal to 1 to j equal to 1 to small n. Capital Fi vector dot del qj ri vector delta qj, this minus double summation over I equal to 1 to capital N, j equal to 1 to small n, pi dot vector dot delta del qj ri vector delta qj equal to 0. Now, this equal to summation over j equal to 1 to small n, capital qj delta qj. This capital qj equal to this summation over I equal to capital N, capital Fi vector dot del qj ri vector minus summation over I equal to 1 to capital N, summation over j equal to 1 to small n, pi vector dot del qj ri vector delta qj equal to 0. Equation 5. This capital qj, this summation over I equal to 1 to capital N, capital Fi vector dot del qj ri vector, and j equal to 1 to up to small n, number of generalized coordinates. This equation 6 is called generalized force, as it plays similar role to capital Fi vector in delta W. Delta W is the virtual work done by the force capital Fi vector. Now, double summation over ij, I runs from 1 to capital N, j runs from 1 to small n, pi vector dot del qj ri vector delta qj, this is equal to double summation over I j ddt of mi ri dot vector dot del qj ri vector minus mi dot vector dot del t of del qj r I vector into delta qj. Because if you derivative this, so dt of this into this, so dt of this means this pi dot into this and this delta qj, and in mi ri dot dot ddt of this. So this. So if we expand this term, so you get this term plus this term, summation of this. And this is equal to double summation ddt of, but note that the double summation I is equal to 1 to capital N, but j equal to 1 to small n here, always. Derivative of this ri dot means vi vector, and this ri dot means vi vector, and derivative of this delta qj, equation 7. Now ri vector is assumed to have continuous second order partial derivative. But we have derivative of del qj ri vector, this equals to del qk, del qj ri vector, derivative of qk plus del t qj ri vector. This we have this. So from this del 2 del qk qj summation of I k equal to 1 to small n into q k dot, this is dot, plus del t of del qj ri vector. So del qj bracket summation of k equal to 1 to n, and this del qk ri vector qk dot plus del t ri vector is equal to del qj, and this equals to terms equal to dt of ri vector. This dt of ri vector vi vector and del qj. So ddt of del qj ri is equal to del qj vi. Vi means dri dt. So this shows that this term equals to this term. So obviously this order of differences with respect to t and q, this t outside dt and the inside is del qj. Here del qj outside and dt is inside here. So the order of differentiation with respect to t and q can be interchanged by the equation 8. Now differentiating 2 partially with respect to q1 dot, q2 dot, qn dot, this is equal to equation 2, this equation 2, this vi equal to this. So we get this del qj dot ri vector dot equal to del qj ri vector, j runs from 1 to small n. This equation 9. Substituting 8 and 9 in 7, this result 8 and this 9 into 7, and we get double summation over I and j's pi dot del qj ri vector delta qj equal to double summation over I and j derivative of mi vi vector dot del qj dot ri dot minus mi vi vector dot del qj derivative of ri vector into delta qj. And after simplification, we get this summation over j, j runs from 1 to small n, derivative of del qj dot capital T minus del qj t into delta qj, expression 10, where capital T is the kinetic energy, summation over I equal to 1 to capital N, half mi vi square is. Then the D'Alembert's principle 5 becomes expression 5. This becomes we get this summation over j equal to 1 to small n qj delta qj minus summation over j equal to 1 to small n dt of del qj dot t minus del qj t into delta qj equal to 0. So we get this summation over dt of this del qj dot t minus del qj t minus capital qj delta qj equal to 0. Equation 11. Since the constants are assumed to be holomorphic, the virtual displacement delta qj are all independent of each other, and hence to satisfy the equation 11, the coefficient of each displacement delta qj should separately vanish. So we get derivative of del qj dot t minus del qj t equal to capital Qj, j equal to 1 to up to small n, expression 12. These n small n equations are known as Lagrange's equation of the motion of the second kind, valid for both conservative and non-conservative, except sliding, friction, etc. system. Now, we derive Lagrange's equation of motion for conservative system. Already you have find this dt of del del qj dot t minus del del qj t equal to capital Qj from this expression 12. J runs from 1 to up to small n is. For a conservative system, external force capital Fi are derivable from scalar potential capital V. V is the function of Ri, R1 vector, R2 vector, Rn vector of positions only, but not generalized velocities. That is R1 dot, R2 dot, Rn dot, not this. So Fi vector is equal to minus grad I V vector. V is the potential energy. That is equals to minus del del Ri vector V, I equal to 1 to capital N, a number of particles in the system. The generalized force Qj is given by Qj equal to summation over I runs from 1 to capital N, capital Fi vector dot del del Qj Ri vector. This equals to summation over del del Ri vector V dot del del Qj Ri vector by 13. So capital Qj vector equal to minus del del Qj V 14, equation 14. From 12, using 14, we obtain ddt of del del Qj dot t minus del del Qj t equal to minus del del Qj v. So this equals to ddt of del del Qj t minus del del Qj t minus v equal to 0, j equal to 1 to small n. If the potential v is a function of position only, so it depends on Qj only, not on Qj dot. So del del Qj dot v equal to 0. So we can write this del del Qj dot t minus v, because del del Qj dot v equal to 0. So we can write this. So t minus v is called L. So we get dt of del del Qj dot L minus del del Qj L equal to 0, where L is the t minus v, the Lagrangian of the system. Equation 15 are usually called the Lagrange's equation of motion for the conservative holonomic system. Explain velocity-dependent potential energy. Lagrange's equation of motion are given by ddt of del del Qj dot t minus del del Qj t equal to capital Qj, and t a function of q1, q2, qn, q1 dot q1, qn dot, and time t is the kinetic energy, and capital Qj is the functions of q1, q2, qn, q1 dot up to qn dot, and t time are generalized forces. The standard form of the Lagrange's equation is ddt of del del Qj dot L minus del del Qj L equal to 0, j equal to 1 to small n, can be deducted from a Lagrangian L, which is a function of q1, q2, qn, q1 dot up to qn dot, and semicolon t, under the following circumstances. If the generalized forces Qj, capital Qj, can be derived from a position-dependent potential energy V, this V is a function of position, this Q1, Q2, Qn, comma T. This capital Qj equal to minus del del Qj V, j equal to 1 to n. Then the Lagrangian L equal to T minus V, position-dependent potential energy. Then L is this form. If the generalized force says capital Qj can be derived from a velocity-dependent potential energy, capital U. So this V is dependent on only the position. This Q1, Q2, Qn, and T. And this is also potential energy, but this depends on the position and also the velocities also. Q1, Q2, Qn, Q1 dot, Qn dot, and comma T. So then this capital Qj equal to minus del del Qj capital U plus ddt of del del Qj dot U, j equal to 1 to n. Then the Lagrangian T equal L equal to T minus capital U. This U is also known as generalized potential. For example, the electromagnetic force, Lorentz force on moving charges, can be derived from the velocity-dependent potential. Thank you for watching this video.